Well, I think we'll get things started. Firstly, welcome everybody to this webinar today, and thank you for giving your time in your obviously busy days, or some of you it might be lunchtime. So just firstly to introduce myself, my name's Peter Finlay. I'm with Geofabrics in the Auckland, New Zealand office. I've been involved with the geosynthetic industry for over 35 years, and with Geofabrics, formerly Macquarie, for just over 30 years. So that's sort of manifest in the grey beard. So I'm currently involved in the development of the containment sector, and in the containment sector we're looking at landfills and wastewater, and products such as geomembranes, GCLs, and of course the Geotube dewatering technology, which is the topic that we're going to be looking at today. Before we get started, just want to mention that this whole session is being recorded and will be posted up on the Geofabrics website in their Academy area shortly after this presentation. And we will run it so that any questions I'll address at the end of the presentation, and so if you please just post anything in the Q&A box, and we'll look at it at the end. So without any further ado, we'll move on. And as I've said, we're going to be talking today about Geotube dewatering technology. So just today it'll be a bit of an overview of the technology, and really looking at the components, what's involved in the whole process, and look at some of the applications where this technology can be used. So there's really two main applications of utilizing geosynthetic containers. The first one is in hydraulic engineering, and this is where you're using these containers are generally sand filled and used for erosion protection works, often in marine and waterway applications, so shoreline erosion protection, breakwaters, groins, that type of thing. The other main application is the use in environmental engineering to contain and dewater slurries, whether it's a waste slurry or a sediment or a contaminated sediment. So a little bit of history, that it was way back in the 1950s that the geotextile containers started being used for the hydraulic engineering applications, so coastal protection works. From there, it was recognized that they could be used for other applications, and the technology evolved. And modifications and developments along the way brought it into the environmental engineering area. And so in the mid-90s and onwards, we saw a lot more use of geotube or geocontainers being used in dewatering of wastes, other wastes and sediments. So I guess most of you will be familiar that there are a lot of there are options available for dewatering. And just firstly, that I know in some engineering, civil engineering applications, when we talk dewatering, people are thinking of dewatering a hole, a building site, a drill hole or something, and that's pumping water out of a site. This is not what we're talking about here. We're talking about dewatering of a sediment, of a solid, to reduce the moisture content of that, and so reduce the volume, and for transporting or taking to landfill. So there are a number of methods out there. There's the mechanical type dewatering, so your centrifuges, your belt presses, and filter presses, and then the more passive, the sludge drying beds. But today we're talking specifically about geotube dewatering containers, or geotube dewatering technologies. And I'll just sort of mention that geotube is a registered trade name of Solmax, formerly Tenkate, and Tenkate were the early developers and adopter of this technology. So what is a geocontainer? It's effectively a flexible, permeable tube with a function to contain the sediment and allow the release of water out through the fabric. So why do we see these products as having good application in here? Firstly, they're able to handle a very large volumes of sludges. They're able to pump a large volume, and often at quite a high rate, into the geotube. You can then achieve very good solids capture. And overall, it's a fairly low capital investment. Probably one of the larger investments is not just the tube itself, but the compound where you'll be laying them down. And an important part, and especially when you're handling contaminated wastes, is that the sludge is effectively concealed from the environment during the whole dewatering process. So the components of geotube dewatering technology, and you'll hear me calling it dewatering technology all along the way, because it actually combines a number of components which all have some importance in there, and a requirement for you to have some knowledge of this when evaluating the suitability for your dewatering project. So I always talk about these four different areas: dredging and pumping. Excuse me, dredging and pumping. Obviously, you're needing to get the sludge from the pond or the source into the geotube. So there has to be some understanding of the equipment required and that type of thing. Then there is the geocontainer itself, and there's quite a lot of technology involved with that, and we'll talk about that. Then there is the compound itself, where you would place the geotube. So we'll talk about that. And then one of the other very important parts of the whole scheme is the sludge conditioning treatment. So the adding of a flocculant to aid dewatering. So firstly, dredging. There's a wide range of options, from the very large cutter suction dredges, which are very suitable for large ponds, wastewater treatment ponds, and that sort of scenario, Then there are the smaller units, which are often very mobile and able to get into more difficult sites. So these types of units for in small waterways, in sediment detention, retention ponds, which need to have the built-up sediment removed. So the geotube itself, so we're dealing with a large tube of geotextile sewn up. So there are some requirements for the geotextile. Obviously, they need to have a certain tensile strength to be able to resist rupturing during the pumping process and with the stresses of holding a consolidating solids material. The function of this fabric is to retain, but also to release water. So there needs to be a very high flow rate through the geotextile. It needs to be very resistant to fabric blinding and clogging, and this comes down to the actual structure of the woven geotextile itself. And the whole aim is to get the fabric which will give the maximum drying effect. So the release of water and able to build up and retain that solids and form a filter cake and allow the release of moisture over time to dewater that sludge. In general terms, for woven geotextiles, there are, I guess, two general types. There's the woven tapes, which is the little picture down there with a cross against it. So the woven tapes are flat tapes, and they have characteristically very small percentage open area, so very low permeability, and they're not going to allow free water movement, and they will clog very quickly. So they're a definite no for this application. So in this application, we'd move towards the woven monofilament, or it might be a multi-filament type of fabric, often giving a more three-dimensional structure. But these types of fabrics will give a high percentage open area, ideal for release of water, but also holding back the fines. So in the construction of the geotube itself, initially the early geotube and other dewatering tubes were longitudinally seamed, so seams along the length of the geotube. This coincided with the roll widths of the geotextiles. But when you're pumping sludge into these types of tubes, there is a lot of forces that are exerted around the circumference. So this is the main stress direction. So a development was to introduce circumferential seaming. So the seaming is taking up some of that stress. And you'll see from this here that there's a bit of technology that goes into the sewing of these seams. They're not a simple pre-air seam that we'll see sometimes on geotextiles on sites. These are multi-thread, high-strength seams. With the, I just mentioned with the circumferential seaming, because you're getting greater strength transfer, it is meant that they've been able to pump the geotubes to a higher height. The other important thing is the filling ports and some developments over time has been some structured filling ports rather than just the elephant's trunks, which initially were a point of potential failures. So the Geotube has a 200 mil GEOPORT for larger Geotube, and a screw-in type of port for the smaller Geotube for a 4-inch or 100 millimeter. And again, this takes away some of the stresses around that fabric port, and means that potentially you can pump higher than other types of geocontainers. The containment compound. This is important because we're obviously pumping material, sludge in there, releasing water. The filtrate has to be channeled back to the water source, or maybe treated. So generally, the containment compound will be first bunded to contain the filtrate that comes out of the geotube. It will have a membrane liner, and that depends on whether the filtrate has contaminants in that. But generally, we'd even see fully welded HDPE liners. In low risk area, maybe just a very thin plastic liner. Drainage, there is a benefit in having a drainage, either a drainage composite or a drainage aggregate along the base underneath the geotube, especially initially when geotube are pumped. There is a lot of water that comes out the lower area of the geotube. So it's an advantage to get that water as quickly away from the base of the geotube. And one of the very important things is the gradient. We would want no gradient across the width of the geotube. And I'll show you a couple of photos in a minute of what happens if there is a gradient. Effectively, you're pumping a lot of water in here and a few solids, and it can be very mobile. So zero gradient across the width, and as close to zero down the length as well. It is even possible for a 30-meter geotube to travel down a cell if there's too much gradient down the length. So here's a typical cell, or this is quite a large one. It was a contaminated canal site, so it was a fully welded 1.5 millimeter HDPE. The buns were 1.5 meters, 2 meters high, and a protection geotextile underneath. So the things that define the containment compound are the I guess amount of sludge that you've got to process. So the number of geotube you require, that's going to affect the sizing. Whether it's a temporary containment or it's going to be used for a long-term purpose, and these are all considerations when designing up the containment compound. So as I've said, if you put geotube on a sloping surface across the width of it, you will get them rolling, or you will get them sliding and getting a banana effect. And if you fill that anymore, it's probably going to end up rolling down into the pond. So very important to get the laydown area as level as possible. There are things that you can do to help keep the geotube in place, but the best thing is to have it as level in all directions. Another sort of compound is something that can be quite mobile, and these sort of mobile dewatering units, or where you're putting a small geotube into a hook bin or a roll-off bin, which can be, once the geotube is, or the sediment is dewatered, the whole unit can be picked up and transported to the dump site. So very good for sites where you might not have a large laydown area, and if you haven't got huge volumes of sludge material. So the all-important question, do we need to treat the sludge before it goes into a geotube? So when I talk about treating it, it's usually the addition of a flocculant and or a coagulant. And everybody will ask, with my sludge from our situation here, can I get away with just pumping it into the geotube? There's a cost in adding a flocculant. Well, unfortunately, in most situations, there is a requirement to add a flocculant or coagulant or both to maximize the dewatering within the geotube and the retention of fines. So there are some situations where no chemical is required. That's more your hydraulic engineering, where you've got coarse sands or gravels, and these will dewater very quickly and reach a 70% plus. So they release the water very quickly. For the finer sediments and organic materials, these are harder to dewater without adding a flocculants. And if you try and pump fine sediments into a geotextile container, you'll get two things. One is blinding off, and the second is you'll get a lot of the fines migrating straight through the fabric. So by treating these finer materials, it brings the fines together and helps retain those and release the filtrate. So here's a nice little example of a food processing wastewater. So a wastewater which has got a lot of suspended solids in there. When you add a coagulant, and a coagulant can be something like your PAC, polyaluminium chloride, which we use a lot in sediment control ponds. I know we do in New Zealand here, for really settling out sediment quicker than it would on its own. So these coagulant will form what the chemists often refer to as pin flocks. So smaller flocks, which are then will settle out over time more quickly than the free sediments. That on its own is not suitable usually to be pumped into a geotube. The small pin flocks are not a strong flock. If you stirred that vigorously, or in the case of going into a geotube, if you pump that, that energy you put in there would break those up, and you would be back to square one, where you've got a lot of fines traveling through the fabric. So the next step is to add a flocculant, and as you can see, that clumps the particles together in bigger clumps, and depending on the type of flocculant, you can get very strong bonding. So that sort of material can be pumped in through a pipeline and into the geotube without breaking up. And of course, you can visually see the separation of the solids from the liquid component. And this liquid is the free water that will very rapidly migrate out through the geotube fabric and be released from the sediment. So what means do we have to look at these and evaluate these? There are a few little tests that have been developed. The first one is the RDT, or rapid dewatering test, which is using the same fabric as the geocontainer is made out of, and the same sludge that you'll take a sample from the in situ site. The second is a little step up, and it's a good demonstration, but it gives you a bit more information as well. The GDT test, which is a small geotube pillow, which holds a few more bucket loads of sludge and gives you a bit more information. The third thing, if you're wanting to get really good information on dewatering times and ultimate results, is to do a small pilot trial. So this is what we refer to as the rapid dewatering test, the RDT. So using a piece of the actual geotube fabric with the treated sludge and pouring that through the fabric. And the objective here is to work out the best combination, really, of matching the fabric with the sludge and the polymer treatment. So you're looking at the effectiveness of the fabric in combination with the best flocculant. And we look for the clarity of water, how quickly that is released. Sometimes with some dosing, you might get very good clarity, but very slow release. And it means playing around with the dosage rates and things to come up with the best combination. And we look at the flock appearance. If it looks like it's a good strong flock that can withstand some mechanical forces to it. And this test can also be used to give an indication of what the ultimate or the short-term percentage solids of the dewatered cake. Well, I hope that didn't come too loud through for some people. It did for me. So this first question of can you put the sludge through there without chemical treatment? And as you'll see, some things straight away. Firstly, a lot of fines travel through straight through the fabric. You will get dewatering, but it'll slow up, and you'll see shortly that it's not moving through the fabric very quickly, and you ultimately get blinding off of the fabric and stopping of the flow. You'll notice that fabric is quite an open fabric. So the next one is with polymer treatment, and also using the GT500, which is the main fabric used in the geotube. So the polymer has been added. This is the energy that's needing to be put into mix the sediment with the treatment, and you'll see a strong flock at the base and some free water. you'll very quickly see the quality of the filtrate. And so that means that we're retaining a very high percentage of the fine materials. So we typically leave that several minutes and allow it to dewater naturally. Here he's giving it a bit of a help along. And as you can see, even with some bit of force there, it's not breaking that apart and getting a lot of sediment through there. So that's what we'd see as a good result in the test. A nice clean filtrate, a good consolidated sample of the sediment, and then you can take that sample and do a dry solids test on it, and that will give you a quick indication of your short-term dewatering, what that sludge can dewater to in over a short period of time. And it may have gone in at 3%, and we may have in a short period got it to 12–15%. This is the little next step up. This is the GDT, the little pillow geotube, and it involves mixing up about 620 litres of sludge, and so it's a bit more involved with it. But as you can see here, it's actually a very good demonstration to show the end client where things work. And I think there's even one chap who's very confident that this is very clean and nice, and he's filling his drink bottle. So here's a little example of this that for a job I did in New Zealand here, a bit of testing. So it was taking a sediment from the quarry sediment pond, adding the flocculent, getting good separation and good strong floc, putting it through the geotube or the GDT, a good filtrate, leaving that to sit out and dry out for several weeks, and then coming through and having a look at it and doing a dry solids test on that. And that gives you a better indication of the time involved to get good overall dewatering. And then the next stage up to do a little pilot test. So sort of what can we expect? And it does depend on the type of solids. With your organic, your biosolids, agricultural sludges, generally these are pumped at very low percentages, and you'll ultimately really probably meet a maximum of 25%. Sometimes they can go a bit higher, but even at that stage, because the biosolids hold on to the water a lot more strongly, at 25%, that sludge will be spadable and truckable without a whole lot of water coming out. So you've reduced its volume significantly for trucking to waste. The other and more mineral and silts and sediments and that, you can often get a lot higher final solids concentration. So greater than 50%, often as high as 70–75%. So in those situations, there's a huge reduction in the volume, again, that you're going to have to take away. So just very quickly, this is the typical overall setup. A sludge source, whether that's pumped from the sludge pond. Often you will have a equalization tank. If you're dredging, the percentage solids in the dredge line can vary from low percentage solids to, if you hit something a bit more dense, a lot higher. So it's an advantage to put it into a tank that it can be mixed, and then a more homogeneous sludge pumped into the geotube. So here we have the polymer setup, a injection pump to inject the polymer into the line. Then that mixing, so some energy put into mixing to make sure that the sediment is fully mixed with the coagulant and the flocculant. Sampling port, very important. That's where you take a sample off and you have a look and you see how well you're getting that mixing and the flocculation of the solids, and then through into the geotube. So little mixing units, you can go right up to very, very big, sort of 8-10 inch in big projects. Sometimes if you're pumping, 200 or 300 meters to the geotube, then there's enough mixing within the pipe itself. So the actual process, here we have effectively jumping ahead, you're pumping to something that's very important, a controlled filling height. So the controlled filling height is the maximum height that a geotube should be pumped to, and this will depend on the size of the geotube. For example, a 27 meter circumference geotube may be pumped as high as 2.7 meters for organic sludges. Why do you never exceed this? Because if you're exceeding that, you're putting extra stresses on the geotextile and the seams. And believe me, if you stand next to a 2.7 high geotube full of wastewater treatment sludge, you don't want to be overstressing it. So this is always your pump. Allow it to dewater, and this may be just leaving it overnight. It may extend as you go through the process, but it's a multiple pumping. Pump, allow it to draw down and dewater, pump again, not exceeding that filling height, allowing it to settle again, and doing the same. And you do this for as many times as it's going to take to effectively fill the geotube. And often that's defined by if in the end you're only pumping for 10 minutes to get a last little bit in, it's becoming inefficient. So you've really reached the capacity. Then you're leaving the geotube on site to dewater and then slowly consolidate over time. And this is the time will be dependent on climate and the sludge, and it's not an overnight thing, especially for organic wastes. It can mean several months on site before it reaches that sort of, say, 25% where it can be excavated and taken to waste. So some of the information we're needing as design inputs is, firstly, what is the sludge? Is it organic, like from municipal wastewater treatment plants, food processing, animal wastes, palm oil, wood processing? They hold their water differently than a sediment involved in sort of mining, stormwater ponds, waterways and contaminated sediments. So this information is really required, and the design really comes down to estimating the size and the number of geotube. And we need to know the sludge properties, which is your volume, how much sludge you've got in situ that you're wanting to process into the geotube. Particle size, is there a percentage of sand going in there? We need to know the specific gravity and relate that to relative density. The site will also dictate the size and number of geotube. If you've got a limited laydown area, it may mean that geotube is not the most suitable thing, product to look at for that application. But if you've got a suitable laydown area, then it's definitely a potential goer. So you've got to have access to water and power for the polymer makedown. The site should be level, or it has to be leveled, and you've got to make that decision if there's a geomembrane required. So just a few briefly, a little brief look at some of the applications. So as I said, you know, we can get very big geotube up to 36 meters circumference and 60 plus meters long, down to small ones that are 5 or 6 meters circumference by 5 or 6 meters long. And these are suitable for these container dewatering, and suitable for sites where you've got limited laydown area and or you need to be mobile. This is some desilting of streams in the Auckland, New Zealand region, and they just have small areas they can set up in one of the parks to have as the containment area. And again, small sites, small dredges pumped into small geotube here on a small temporary laydown pad, and these sediments often settle out and dewater very quickly to a nice consistency that the tube is split open, and then that's excavated and trucked to landfill if it's contaminated, or another site where it can be disposed of. But when you get everything right with the polymer, the pumping and everything, even on small ones, it's quite impressive the rate the filtrate comes out there and the quality of it. So then we can go up to large sites. Big mining sites, it's not so big for us in New Zealand. I think this is a New Zealand job, but in other countries where mining is much more prevalent, there are good applications here. And here you'll see that they're actually stacking the geotube. There are some special requirements, and it's too much to go in this presentation, which I'm getting fairly close to time. But there is techniques you're able to employ to stack geotube one on top of the other, and this is generally done with mineral waste more than organic waste, because you need to get this to greater than 50% solids, so you've got some support for the top tubes. Wastewater treatment plants, cut a suction dredge. A young fella there who doesn't have a white beard, but is very confident standing on a geotube that's been pumped to 2.7 meters high and now settling nicely. Industrial sites. This is a wood processing wastewater treatment sludge. This is a sand washing sludge material being pumped in here. And again, environmental, big potential for decontamination or desilting contaminated sites, whether it's a lake or a pond or here a canal. And this is a canal that was contaminated with dioxin. So it's an important project for us in the Bay of Plenty in New Zealand. Oh, excuse me, sorry about that. So just finally, there are a wide range of applications that Geotube technology can be used. Obviously, anywhere where there's a wastewater treatment pond, whether it's a municipal sewage treatment plant, a food processing, agricultural, dairy farm effluent, industrial wastewater, they're all applications where the geotube can be used. And then in the mineral area, obviously mining, sediment ponds, cleaning out waterways, remediation, and contaminated materials. So I know that's a fairly quick run through, and I was told to be finished about 10:02, so that's good. So I see there's a couple of questions in the Q&A, so I'll just have a look here. Okay, we've got 2 questions. Now, the first one's a fairly difficult one, which says, which polymer is recommended to treat crude oil waste? Now, I'm not a chemist and a polymer expert. I tend to get the experts involved from people like Exxon or Chemiplas, and New Zealand and Australia will have their own specialist companies there, because it takes a bit of looking at the charge on them, the material, and so look, I can't really answer that, but I know there is possibly a type of polymer that can be used in there. And then another question here, or maybe a bit more of a statement, is this is good for a gold mine instead of using tailings to the sea? Look, very definitely. And gold mine, coal mines, we've done a number of projects, not so much in New Zealand, but I went to a large coal mine project in Atlanta in the States, and that was using hundreds of geotube, and that was specifically for taking desilting all the tailings ponds so that they didn't get overflow into neighbouring waterways. Another question I have here is, can the geotube be reused? Now that's the second most asked question after, do I need to add polymer? The answer is no. And when you've seen a geotube, especially the large ones on site, and as I said, pumped to near 3 meters high, the fabric's been put under stress. I don't think anyone's going to want to guarantee if you empty it out that you use it again. Plus, there will always be some clogging of the geotextiles. So really, they get used once. Typically, the geotube will be, once it's fully consolidated and reached the desired percentage solids, then it'll be slit open and carted to waste. The other option is it can be left in situ and covered over. So there are sites, and that contaminated canal site in New Zealand, that compound was then fully covered over and planted into to complete the treatment of the dioxin. So that's really, it's the last question. I thought I had one more, but I just have a thank you for the presentation, Peter, from Matthew Montai. So thank you. So look, unless there's any questions, thank you very much for attending and taking your time out of your busy day. And, I hope you have got something out of it. And really, if you've got more questions, I can be contacted through Geofabrics, and in Australia, Geofabrics have some people with very specialist and good knowledge for answering your questions on Geotube dewatering technology, and they also utilize their own laboratory to do some of the polymer testing if you require that. So thank you very much for your attendance, and yeah, I'll welcome any questions that follow by email. Thank you very much.